Now, we'd like to be able to go a little further with it and to see if we could actually get an algebraic expression that relates these microscopic quantities to the speed of sound in a material. And to do that, we need to be a little more quantitative about the behavior of masses and springs. And you saw it when we ran that things were oscillating, bouncing back and forth. And you doing experiments with springs this week in lab? Or is that you are? You are. Okay. So you're hanging masses on the end of springs and you're letting them oscillate and you're measuring periods and spring stiffnesses and okay. So we want to do something here. We want to see if we can actually get what we call an analytical expression that describes the motion of a mass on a spring when we not just hang it there to measure a spring stiffness, but when we actually let it oscillate. And to do that, we're going to go back to the momentum principle. And we're going to apply the momentum principle to the system of a mass and a spring in a slightly different way than we've done before. We've been writing, so let's write this. Let's remind ourselves about the spring force. We have a spring force, a force exerted by a spring is minus k sub s times the stretch in the L hat direction, where L hat is a vector that points from the fixed end to the movable end. We're going to consider, for simplicity, we're going to consider horizontal mass spring systems. So a block attached to a spring which is anchored on a wall, sliding on some very low friction surface. So friction is negligible here. So maybe like an air track, a cushion of air, an air table. And it's the reason we're going to do this is it's just algebraically simpler than considering the vertical case where we have to take into account the gravitational force as well as the spring force. It turns out the solution ends up being exactly the same, and the solution, it's solved at the end of the chapter to show you that. And so what we want to be able to do is we want to be able to write an expression for the location of the end of the spring as a function of time valid at any time. So we want to be able to write a function x of t equals. Okay, so that's our goal. And we're going to start out with the momentum principle, of course. So we have delta P is F net delta T, one of the ways we've written the momentum principle. This is a case where the force is going to be continually changing as the mass oscillates back and forth. And since we want it as a function of time at any time, we'd like to have this in an expression that gives us instantaneous information. So we're just going to rewrite this as change of momentum, the ratio of delta P to delta T is F net, and then we'll just take the limit as our time interval goes to 0. And so, of course, what we get is a derivative. So we get dp dt equals F net. The rate of change of momentum of our system at any instant is equal to the net force applied by the system at that instant. So this is the instantaneous version of the momentum principle. Okay, so what does this mean? Well, we've got the time rate of change of 1 over 1 minus the square root of the magnitude of V over C squared mv equals F net. And at high speeds, this is a messy expression because the direction and the magnitude of V can be changing, so gamma is also changing, so you need the product rule applied several times in it, and it looks fairly messy. Because we're working in a system that's not moving fast compared to the speed of light, we'll use the approximate form, and we'll say dp dt is approximately equal to the rate of change of 1 times mv, where gamma is approximately 1. And so if we work this out, of course, we get the rate of change of the mass times v plus the mass times the rate of change of velocity. And in most situations, the mass of our system isn't changing, which is convenient, so we're going to only consider that situations where that's 0. And so we're going to approximate the rate of change of momentum by m dv dt. Now, that may look somewhat familiar because, in fact, the rate of change of velocity has a name. We mentioned it once before. It's acceleration. So the rate of change of velocity is defined as acceleration. That's a vector. And what does a derivative of a vector look like? Well, remember that something like dp dt is just going to be a vector itself. It's the rate of change of the x component, the rate of change of the y component, the rate of change of the z component. This expression, we'll write approximately equal because it's not completely true. This expression is sometimes written as the mass times the acceleration, and that may be familiar to many of you from high school. It too is a vector equation. It's only approximately correct. At low speeds, it's a very good approximation. At high speeds, it's not a very good approximation. And so this expression here, dp dt equals F net, is, of course, 3 separate equations. It's dpx dt equals F net x, dpy dt equals F net y, etc. So what we want to do is apply this form of the momentum principle to our mass spring system and see where we can get with it. So what we need to do is we need to we're going to need to write work on both sides of the equation. And in general, when we're solving a problem involving this form of the momentum principle, the idea is to work on the left-hand side of the equation as much as you can, fill out the right-hand side of the equation as much as you can, see what's left over. That's probably going to be your unknown, and solve for it. So we need to write an expression for the force on this object connected to the spring. And so we're going to need, let's say that the relaxed length of the spring here is, this length is L0, and the mass is going to be somewhere here. So we need the vector L, which of course is that. And so the vector L hat goes that way. And so we can write the force, the spring force on this mass is equal to minus the spring stiffness times the stretch times L hat. And by inspection, we see that L hat in this case is 100. So it's going to be equal to minus K sub S times the stretch, which is going to be the magnitude of L minus L0 times 100. So we're only getting action from the spring in the x direction. Now it is true that there are other forces on the mass. There's the gravitational force due to the Earth pulling down. There's the force of the air cushion it's riding on, or the water cushion pushing up. But since the momentum of the mass is not changing in the y direction, we can conclude that those forces are equal and opposite and not worry very much about it. Now we can make our life very much simpler mathematically by choosing an origin in a convenient way. So what we're going to do here is we're going to say that we're going to put x equals 0 at the end of the spring when it's relaxed length. Okay, so the coordinate of this would then be some x here. So we can use the spring force. In fact, let's just write the x component here. So F spring x is minus the spring stiffness times the current length of the spring minus L0. Well, the current length of the spring looks like it's going to be, L is going to be L0 plus x, the way we've set up our coordinate system. So we've got an L0 plus x minus L0. And so, in fact, this simplifies down to the force, the x component of the force is minus k sub s. These L0s cancel, and we just have times x, which just makes this mathematically simpler and easier to deal with. So that's the F net side of the equation here. So we have a minus k sub s times x, and now we need to write something about dpx dt. And that's a changing quantity, but we can use the simplification we talked about a moment earlier and say that dpx dt is approximately equal to mass times vx, dvx dt. But velocity is the rate of change of position. So v sub x is actually dx dt. So we have m times the rate of change of the velocity v sub x, which is itself dx dt. So we've ended up with a second derivative here. So we've got dpx dt at low speeds, mass not changing, is m, second derivative of x with respect to t. So we'll write this over here. We have m, second derivative of x with respect to t, and the moment, that's what we've gotten to with the momentum principle for this system. Now, at least some of you are probably far enough along in math that you know what kind of an equation this is. It's a differential equation, isn't it? And one of the ways of, there are a number of techniques for solving differential equations, but one of the most powerful and useful techniques is actually just to guess a solution based on the properties of the equation. And so what we have here, we can rewrite this as second derivative of x with respect to t is equal to minus k sub s over m times x. So the second derivative of the function x of t is equal to a constant times itself. So we need a function whose second derivative brings us back to that function. Trig functions, sine or cosine. Yep. So in this particular, so let's guess. So one thing you do is you guess. So we're going to guess the following thing. We're going to guess, we guess that x as a function of t is the cosine of something whose argument varies with time. So there's got to be a t in the argument of this cosine function. And then there's some factor that we usually call omega. This is not a w, it's lowercase Greek omega. And cosine only has values between 1 and -1, and sometimes springs, the position of a spring might be something other than 1 or -1, so we just need a scale factor here, and that's typically called a, the amplitude. So that's our guess. And now what we do is just plug it into this equation and see what falls out. So we say, we guess this, let's try differentiating it. So the second derivative with respect to time of a times the cosine of omega t is equal to minus spring stiffness over the mass times a times the cosine of omega t. What's the second derivative with respect to time of a cosine omega t? So the first derivative, cosine is negative sine. So then we differentiate that again. We're back to cosine. So we have this minus. We're back to cosine omega t. A is a constant. And there's one other piece. Omega squared. Right. And that's equal to minus k sub s over m, a cosine omega t. And now we see that a big chunk of each side of this equation is the same. So a cosine omega t and a cosine omega t are the same. And that leaves us with the conclusion that this actually works if omega squared is the spring stiffness divided by the mass attached to this thing. So we get x as a function of t is a times the cosine of omega t, where omega is equal to the square root of the spring stiffness over the mass attached to this. So that should allow us to predict position anywhere. Now let's just look at this equation for a minute and see what the pieces are. So this x is position in meters, right? So this better have meters attached to it. This is, of course, seconds. The argument of cosine is unitless. So this better be inverse seconds. So it's really radians per second. So omega is what's called the angular frequency in radians per second. So we have its units of our radians per second. It's called the angular frequency. Angular because there's radians in there. And if we plot the position, the x versus t for this mass as it's oscillating back and forth, Okay, so if this is x, this is t. It should do something like this, assuming that there truly is no friction. If there is friction, of course, it's going to die down. And so this time to go from one back to its original position is called capital T. It's the period in seconds. And this height, this maximum displacement here from 0, that's A, it's called the amplitude. And so there are various relationships that we can work out here because of this. If this oscillation goes through omega radians in 1 second, in one period where it's gone all the way from where it started back to another, it should have gone 2 pi radians. So it looks like omega should be 2 pi over the period, 2 pi radians in t seconds. And so we can all, ring changes on this. The period is 2 pi over omega. There's also another thing called the frequency and number of complete cycles per second, and that's just 1 over t. So that's frequency. Okay. So we actually solved the differential equation, and we got, we actually came up with an equation that'll predict the behavior of a spring attached to a mass, oscillating a mass, as a function of time forever and ever, as long as there's no friction. The amplitude says how far the maximum displacement. Omega is the angular frequency. That tells us how fast or slow it's bouncing back and forth. So we ought to be able to make some predictions and answer some questions about this. So let's, what? Well, notice that it just depends on where you start. Okay, so let's consider this vertical mass spring. Right now, its initial displacement is 0. It's just hanging here. If I started by stretching it, then I've started with an initial non-zero amplitude, and so it comes back. So that's going to be a cosine. If I want to start here, I'm going to have to start with 0 stretch but non-zero momentum. So probably what has to happen, I have to start at this point with a kick downwards. And that would be a sine, but it's really a matter of just shifting over, and so just a... Okay. So let's see if we can make some predictions just based on this about what we'd observe here. So we have, and let me say again, it works out that for the vertical mass spring oscillator, the same equation works. It's going to be y of t, of course, is going to be cosine omega t. Omega is still the spring stiffness over the square root of the spring stiffness over the mass. And it turns out there's just kind of an offset in your coordinate system because of the gravitational force, but so it does work. So based on this equation here, looking at our equation for x as a function of time, let's see if we can just predict some things. Suppose that we have a mass on a spring that makes one complete round trip in 1 second. So the period's 1 second, probably about like that. Now suppose we put 2 masses on it. What should happen to the period? Oh, we lost all those equations, didn't we? Let's write them over here. So omega is 2 pi over the period. So the period is, of course, omega over 2 pi. Well, period is 2 pi over omega, right? And the frequency is 1 over the period. Okay, so definitely not 3. Nobody likes 3, but so I heard you talking about it in pretty sensible ways. So if the period is 2 pi over the angular frequency, then that's 2 pi divided by the square root of the spring stiffness over the mass, or 2 pi times the square root of the mass over the spring stiffness, 1 over omega. So if we double the mass, then it looks like the period should get longer by the factor of square root of 2. Yep. So square root of 2 times, what's square root of 2? 1.4. So it looks like it should indeed be 1.4 times 1 second, so 4. Okay, questions about that? So you're right that the period goes up, but you have to actually look at the algebraic expressions we've got. Okay, questions about that? So have you tried this in lab, doubling the mass, looking at the changes in period? Yeah. Try it. Okay, what's going to happen if we double the spring stiffness? Okay, 2. Yes, and how did you get it was a factor of 0.7? Because we had period was 2 pi m over k sub s. So if we have a 2 here, and we're dividing by the square root of 2, aren't we? So 1 over square root time, the period times 1 over square root of 2. Okay, questions about this? Okay, here's one here's one to think about. Again, you have to take the equations we've got very seriously in answering this question. So the question is, we often start a mass spring by stretching it a certain amount, and that determines the amplitude. What happens to the period if we double the amplitude? Okay, we've got a real solution, so take the analytical solution we came up with very seriously. All the information you need is in that equation. Okay, well, so the most popular answer is indeed 3, 1 second, but we have some people voting for other things. But 3 is correct. Would somebody like to say why, who said that, say why you thought that was correct? Sure, yeah. It's not in the equation. That's exactly right. The period depends on the angular frequency, which is k sub s over m. There isn't any a in there. There isn't any a in there. So that if it did depend on the amplitude, the period depended on the amplitude, we'd have to have some a in that argument of the cosine function. And the fact that it doesn't means that that dependence isn't there. So what's not in an equation turns out to be just as important as what is in an equation. So that's a very special property of these mass spring systems. This an oscillator that behaves that way is called a harmonic oscillator, and it's very interesting that the period doesn't depend on the amplitude. If you increase the amplitude, it's got farther to go in one period. So why doesn't it take longer? Because it's going faster during a lot of it. So a harmonic oscillator is very special. Not all oscillators are like that. It's actually why grandfather clocks work, because as they wind down, even though the pendulum swing gets smaller in amplitude, the period stays the same. Okay, so we have this spring mass oscillator here, and it's got a period of 1 second. And now we take it to some incredibly massive planet where the gravitational force is much larger. So the value of little g is twice as big. What happens to the period? All right. You've got the basic idea. So we don't see any g's in this equation, do we? So you're absolutely right. Doesn't depend on that. Okay, good.